Hi, my name is Craig Lefkowitz. I'm a senior developer advocate with AWS CloudFormation, and I'm going to talk about building your first AWS CloudFormation resource provider. We'll start with what resource providers are and when you use them with CloudFormation. We'll talk about the building blocks and tools that you'll use with resource providers. Lastly, we'll walk through a typical development and operational pattern and then end with a demo. So let's start with the typical pattern for creating resources with CloudFormation. You start with authoring code that's written in YAML or JSON. That code is then uploaded using your browser, or in more modern DevOps approaches, you could be publishing code to a repository as part of a CI/CD pipeline. The code is then executed and resources are deployed. So let's focus on some coding scenarios. CloudFormation templates are written in YAML or JSON, and they come with a core set of functionality, parameters, resources, mappings, and outputs. You also have the ability to author macros in order to provide abstractions and shortcuts. The Serverless Application Model, or SAM, is a great example of this. You can also provision resources in CloudFormation using popular coding languages such as Python or Go, using the AWS Cloud Development Kit, or CDK. And lastly, and what we're going to focus on in this session are resource types, which is an extension to CloudFormation that allows management of third-party resources such as New Relic alerts or Dynatrace agents, for example, or really any resource that you'd like to manage. If there's something that you want to manage with CloudFormation and the native AWS type doesn't exist, you should be looking at resource types. So resource types are CloudFormation resources that can be authored by anyone and then used in CloudFormation templates. Just like the service teams here at AWS author an EC2 instance resource or an S3 bucket resource, you can do the same thing. Resource types that you author are first-class objects, which means that to the CloudFormation engine, a resource type that you author in a native AWS resource is almost indistinguishable to the CloudFormation engine. And that's because we're all using the same framework. This allows tighter integration with CloudFormation features, such as drift detection and resource import, as well as other AWS services such as AWS Config. Resource types have some distinct features, such as the registry, which is a centralized repository where resource types are stored, as well as other technical details that we'll get to in a bit. So you may be familiar with custom resources, which is a feature we introduced in 2015 that enables CloudFormation to manage non-native AWS resources. Resource providers work a little bit differently. So as an author of a resource type, you're going to start with writing a schema file that defines your resource. There are inputs and outputs in that schema file. There's some metadata such as IAM permissions. You also author handler code that handles 5 CloudFormation actions, which is create, update, delete, read, and list. The code and the schema is packaged and submitted to the CloudFormation registry. Once in the registry, it's then available to use in a CloudFormation template by any consumer in your organization to provision and manage the resources that you define in your code. Some notable differences from custom resources are that the handler code is executed in the CloudFormation service account. You no longer have to manage the Lambda function that backs your resource. Authoring a resource type starts with defining a schema, which enforces strong typing. This allows for greater integration with other AWS services. Resource types have configurable timeouts, providing greater control on your resource's lifecycle. We provide a command line tool that accelerates development by providing scaffolding, testing, and provisioning tools. And resource types use the CloudFormation registry, which is a centralized version repository that allows you to easily share your resource across templates. So there are 3 major components of a resource type. First is the registry, which is a version repository where resource types are stored. Second is the CloudFormation CLI, which is an open source command line tool that helps with the development of resource types and registers them for use with CloudFormation. It includes commands to enable each step of creating your resource types, and we'll get into that detail a little bit later in this presentation. Up on the screen, I have a QR code that links to the CloudFormation CLI GitHub repository that you can view later. The CloudFormation CLI was designed to be language agnostic through the use of a core library. Today, the CloudFormation CLI officially supports 3 language plugins, Java, Python, and Go, but it can be extended to use any language through the use of the plugin system. More detail is available in our GitHub repository. So as I mentioned in the previous slide, once you author a resource type, you submit them to the CloudFormation registry. The registry is where resource types are stored, both resources that you develop, as well as the native AWS resource types. Native AWS resource types that are authored by AWS are labeled public. Resource types that you develop are labeled private. In the console displayed, I've filtered by private types in the dropdown, so I see the private types that have been registered to my account. If I click one of those types, I can see additional information on that type, such as the schema and the version. Remember that the registry is a versioned repository. Detailed information on your resource type can be viewed in the console like you see here, as well as through the API. So let's talk a little bit about the CloudFormation CLI, which is an open source tool that provides a consistent way to model and provision resource types through CloudFormation. It includes commands to enable each step of creating your extensions. It's installed through PyPy and provides several commands that assist with developing, testing, and submitting resource types. It also has commands to initialize the scaffolding for a new project, run contract tests, and submit your resource type to the registry. So let's run through a typical development pattern. The first thing you're going to do after creating a blank directory for development is to run the cfn init command. This command creates the scaffolding code and directory structure for a resource type project. Once the project has been initialized, you'll define your model, which is a JSON file in the root of your directory named after the name of your resource type. This is also called the schema. You then author your handler code, which is located in a directory specific to the language you're developing in. This code contains logic for the 5 CloudFormation actions, which are create, update, delete, read, and list. We'll talk about those actions in more detail in a bit. So after authoring your handler logic, you'll want to run cfn generate to update the auto-generated files in your project. You'll build your code as you normally do, depending on the language you're developing in. And after your code is built, run cfn tests to perform contract tests against your handler code. Once you're satisfied that your code passes, you'll package and submit your code to the CloudFormation registry using the cfn submit command. Note that I've used a set default switch, which sets the version I'm submitting as the default version. Remember that the CloudFormation registry is a versioned repository, and only one version can be active at any given time. The set default command sets this version as the active version, and this is the version that any future CloudFormation templates will use. Then, test your code by submitting your template that references your resource type, fix any issues that you encounter, and then repeat the process. So one of the first things you'll do when developing a resource type is model your resource by authoring a resource schema. This is that JSON file in the root of your project's directory that's named after your resource. We're looking at an example of a resource named AWS Utility CloudFormation Command Runner. The first section is the properties, which define the inputs. In this example, we see a single input named command, which is of type string. Next, you'll define the outputs of your resource type, which are the attributes that a user of your resource type would access through the getAtIntrinsic function. These are defined in the read-only properties section. Here we see that there are 2 attributes, one named output and the other ID. Moving on to the handler section, here you're going to list the handlers that your resource type will process. You don't have to implement all of the CloudFormation actions. For example, you can specify that your resource provider handles only create, read, and delete, but not update. In this case, when CloudFormation attempts to perform an update on your resource, it will replace your resource by creating a new resource and deleting the existing one. You'll also define the IAM permissions each handler requires. In this example, the create handler requires the EC2 describe subnets permission. By defining the permissions your resource handler requires, you inform users of your resource the minimum set of permissions needed to implement your resource. So let's take a deeper look at those permissions in the resource type schema. In each CloudFormation action that your resource type handles, you should specify the IAM permissions that it needs to perform that action. This provides users of your resource type to definitively know the exact permissions your resource type requires. Using the CFN generate command, you can create a CloudFormation template that provisions an IAM role with the permissions defined in your resource schema. The CFN generate command will create a file called resource-role.yaml in the root of your project that provisions that IAM role. This role can be used to assign an execution role to your resource. If assigned, CloudFormation will use the execution role to provision any AWS resources in your resource type. Otherwise, CloudFormation will use the permissions of the user calling the resource type. Assigning an execution role can be a handy way to allow operators to use your resource type without having to directly grant them an IAM role that would otherwise be overly permissive. For example, let's say that your resource type requires that all IAM permissions for EC2 need to be present. So you can assign an execution role to the resource type that grants that permission. A user that uses your resource type in a template wouldn't need any EC2 permissions for it to work. So let's talk a little bit about the handlers. There are 5 actions that CloudFormation can send to your resource type to handle. You're likely familiar with 3 of them, namely create, update, and delete. However, there are 2 actions that you may not be, read and list. The read action is used for getting attributes of your resource, for example, when a user calls the getAtIntrinsic function. It's also used if a user wants to import an existing resource into their CloudFormation template, or it can be used for drift detection. In this case, CloudFormation will request the properties of the existing resource in order to perform those actions. List is an action that will be used in future use cases. One such use case is when a user or system wants to list multiple existing resources that can be used for a bulk resource import operation. So there are some things that you want to consider when developing your resources, is that each handler has a single entry point. That doesn't mean that the code for your handler has to be implemented entirely in that entry point. It can be dispatched to another function or class that's located in a separate file. Handlers must not leak resources. Keep track of the resources that you create so that when a delete action is passed to your resource type, it will delete all the resources you've provisioned. A handler must return a progress event within 60 seconds or it's going to be marked as failed and rolled back. So what if you need more time? You can use callbacks, which we'll cover in a bit. So let's first talk about what a progress event is before getting to callbacks. A progress event is a JSON object that's always returned from your handler. The progress event describes the status of your resource, which is either success, failed, or in progress. If the creation of your resource is successful, set the operation status to success. If you set the status to success, CloudFormation will mark the resource as successfully provisioned and will continue processing other resources in the template. In the event that you encounter an error, you'll set operation status to failed and set the appropriate handler error code. In this case, CloudFormation will mark the resource as failed and will roll back. Remember to always set the message to something descriptive and actionable so that the user has visibility into what's happening. So let's get into those callbacks. This is what you're going to use if your code needs more than 60 seconds to provision your resource. Here we see handler code returning a progress event with an in-progress operation status. The progress event is set with a callback delay of 300 seconds and a callback context, which is any state that you'd like returned when CloudFormation reinvokes your handler. Remember, your code is being executed in a Lambda function and is stateless. The callback context allows state to be passed back. In 300 seconds, CloudFormation will call your resource handler code again, along with your callback context object. Your handler code executes its logic, and if it needs more time, it can again return the progress event and an in-progress operation status. CloudFormation will continue this cycle up to the limit set in the timeout in minutes property that's in your schema file, up to a max of 36 hours. If the timeout in minutes property is not defined, it defaults to 2 hours. When your handler code has reached a terminal state, you'll return an operation status of success or failure, signaling to CloudFormation that your resource has completed and what it should do next, either mark the resource as complete or roll back. So let's switch gears here and we'll talk about some operational patterns. If you encounter an error during execution of your handler code, you should return a progress event with an operation status value of failed, a handler error code, and a message that's passed back to the user in the form of a status reason. In this example, we inform the user that we encountered a 400 bad requests during execution. And you can see from the GUI in the status reason column that 400 bad requests message is displayed to the user. You can also send logs to CloudWatch. The log group is named after your resource type using the following format: namespace, service name, resource name, logs. And here we have an example on the screen with an AWS utility CloudFormation command runner resource that's in the log group. If you use the CFN submit tool to submit your resource type, logging is automatically enabled. If you use the AWS CLI to register your type, you must use the logging config option to turn on logging. And those are the basics you'll need to create your first resource provider. Before getting into the demo, I'd like to call out some notable examples of resource providers being used today. As I said before, the service teams here at AWS are authoring their resource providers using the same resource provider framework we're talking about today. The AWS Quick Starts team has a resource provider to manage Helm on EKS, as well as partners such as MongoDB, New Relic, and Dynatrace, to name a few. And with that, let's get into the demo. I'm going to show you a resource type that was written by AWS support called command runner. This resource type takes a bash command as input, runs it, and stores the output as an attribute that can be referenced in your template. This resource type has a number of use cases. For example, if you wanted to perform some complex math operations or perform advanced string manipulation, you can do that pretty simply by writing the appropriate bash commands, and then you could reference the output of those bash commands in your template. We wrote a blog about it, which is here on the screen. It has a nice diagram that shows how this all works. It also has an example where we calculate the number of IOPS for an EBS volume based on its size. I have a QR code up on the screen so that you can read it later. So if we look at the diagram of how this works under the hood, we see that the command runner resource type spins up an EC2 instance. It runs the bash command on the instance. The output is stored, and then the instance is terminated. So if you remember from the slides that I talked about, resource types must return their status within 60 seconds, or CloudFormation is going to mark that resource as timed out. The stack could then be rolled back. But spinning up an EC2 instance usually takes longer than the 60-second window. This is a case where we use callbacks to get around that 60-second limit. So let's take a look at the code, which is available on GitHub. The link to the GitHub repository is in the blog. So I'm going to grab the link here. We're going to clone the repo. We're going to open up a VS Code window. All right. So if we look in the source directory, this code was written in Java. We have 3 handlers for 3 CloudFormation actions: create, delete, and read. We're going to look at the create handler code. This handler has an entry point here at line 49. It's the create handler class. And one of the first things that we do when this handler is invoked is we check for callback context. If the callback context is null, we know that this is the first invocation of the create handler. And what we do is some checks and validations to ensure that the caller has the right permissions, that other things are in the right state, before we provision that EC2 instance. Provisioning the instance is a relatively expensive call, so we want to make sure that everything is in place before we spin that EC2 instance up. So if we look at one of the first checks that we do, we check to see if the caller has the terminate instances permission. So we check that by running a policy simulation, and if that simulation fails, we're going to return a progress event with a status of failed, along with an error code of invalid request and a descriptive message letting the user know what happened and how to fix the issue. We run a number of other checks and validations but we're just going to assume that everything passes. If it does, we end up here on line 258, where we invoke the CloudFormation create stack API. So, and in this code, we're using CloudFormation to manage the lifecycle and to provision that EC2 resource. Immediately after creating the stack to provision the EC2 instance, we're going to return a progress event with a status of in progress. We're going to set a callback delay of 90 seconds. And we're also going to set a callback context that contains the stack name and the stack ID. So after 90 seconds, CloudFormation is going to re-invoke this create handler. So we're going to end up back here at the entry point. This time, though, the callback context is not going to be null. It's going to have the stack name and stack ID that we set earlier. So what's going to happen is we're going to end up in this else block on this invocation. One of the first things we do here is we get that stack name from the callback context. And we're going to do a CloudFormation describe stacks API call to get the provisioning status of that EC2 instance. We want to know if that EC2 instance has been successfully provisioned and that the bash command has completed its work and that we received the output. And that would be the case if we've reached a terminal state. So if we've reached a terminal state, that means that either things have gone really well and we have a terminal state of create complete. It also can mean that that something went wrong. And in that case, we would see that the stack has a status of create failed or potentially rollback. So if we've reached a terminal state, we determine which state we've ended up in. If it's reached a state of create complete, that means that the EC2 instance successfully provisioned, the bash command ran, and everything worked out as we intended, and we reached the end of the happy path. And in that case, we're going to return a progress event of success, which means that CloudFormation is going to mark the resource as successfully provisioned, and it's going to continue provisioning any other resource you have in that stack. If, however, we reached a terminal state where something went wrong, where the stack did not provision the EC2 instance, there's an error. That means that we reached a terminal state where the stack status is either create failed or it might be rolled back. And in that case, we're going to return a progress event with a status of failed. We're going to set an error code of not stabilized, as well as provide a descriptive message to the user letting them know what happened and what next steps they should take to debug. Here we provide the stack name so that they can go and investigate what happened to that EC2 instance. Okay. However, it's possible that the EC2 instance has not reached that terminal state, that the instance is still running. Maybe there's some complex bash code that needs a little bit more time, and in that case, we're going to end up here. In this case, it means that we still need a little bit more time to let that EC2 instance finish its work. So here we're going to return a progress event with a status of in progress. We're going to set a callback delay of 30 seconds this time. We're also going to set that callback context again with the stack name and the stack ID. At this point, CloudFormation waits 30 seconds, and then it's going to re-invoke the create handler again. So we can continue returning in progress for up to 2 hours by default, up to a maximum of 36 hours. The length of that timeout is set in the schema file. The name of the property that defines that timeout is called timeout in minutes. And that's the quick demo of the command runner resource type. It's an example of a resource type that uses callbacks. If you'd like to inspect the code, it's in GitHub. Just use the QR code at the beginning of this demo to navigate to the blog, and the GitHub, the link is in that blog. So if you'd like to see enhancements to this resource type, or if you have any issues with using it or provisioning it, we encourage you to submit an issue in the repo or a pull request. So that's it. So thanks again for your time. Please remember to fill out your session survey.